Welcome again to this lesson 7B. We continue with, and I would like you to have ensured that you are done with lesson 7A, which I'll be shortly sending. In fact, if we are lucky, I may have to send both so that you are able to continue within the time frame that you have. We talked about the heritability, and then we went into the issue of the selection response, and then, of course, it involved the breeder's equation. And I did emphasize that we are talking about a genetic gain in terms of the rate of genetic gain. It changes. It's not an equation where it resolves into a single value. And this is probably the best example that should be answering the difference between selection response and rate of genetic gain. They are slightly different. For example, some organism was studied. I don't know if it was a snail or something, but it doesn't matter. And we see that it was studied across 13 days. That's about a 2-week period. And we see that in day 1, when the selection began to be done, that from the control, which was 92.1 micrometers, then the selection was basically 92.1 millimeters. And as you can see, and in the brackets, we have the standard deviation indicated, that basically that was day 1. Control and selected was the same because that was the population that was grown and it was the control that was already selected to be studied. Then 4 days afterwards, we see the growing shell length. And in the growing shell length, out of the control, then what had been selected was slightly higher. You can see 4 days. The control then compared to what was selected was lower and the selected was higher. Then after 1 week, when looked at what was the control from which the selected was done, the selected was 136.4. And then when we get to 10 days, you can see that from the control, which was changing over a period of time, out of them, we had some that were actually selected that had 150. And after 2 weeks, we had a selection that compared to the control was actually 10 units higher in terms of the shell length. So in the calculation of the response, you can see over that time, the response had a mean of 9.2. 9.2. And you can see the changing values of the selection response. It is not the same as the genetic gain, because you can see the rate of genetic gain is actually differing 2.9 genetic gain was 2.6%. 9 response at 7 days was 7.06%. So basically, here we can see that they are saying different things, basically different things. You can see that the genetic gain and the response are not the same values. Think about it, because the genetic gain has a different formula and the response has a different formula as well. So again, these are going to be expected to be different. Now, so we have this bell-shaped curve, and we are looking at a selection where the arrow points, where you are looking at a selection from the mean. So we have a sample mean from the mean that we see here as 10. The genetic gain that we have just seen in this is calculated by this formula, and it is very important for us to see how that formula is closely related to the issue of the breeder equation or favorite equation. We have the selection intensity there. We have the length of the cycle interval. Remember that formula with this, the heritability by the sigma p and the I over the L. Now, the heritability, as you can see, is where, in the narrow sense, you get the additive from which we subtract the epistasis, the dominance, and the genotype. And in the phenotype, we have the genotypic variance, total, we have the environmental variance, we have the G by E variance, and we have the error. They constitute the sigma p, the sigma squared p. So this is basically what happens. That formula is extremely important, very, very important for us to recognize as representing the genetic gain, the rate of the genetic gain. It's a slightly different formula from the calculation of R, the response to selection. So really here we see this figure showing the genetic gain and the expansion of its terms to fundamental parameters of the quantitative genetics. This is clearly an oversimplification of the advanced genetic, quantitative genetic principles employed in plant breeding. But the genetic gain effectively relates to 4 core factors that influence plant breeding. We have to notice those 4. 1, the degree of phenotypic variation present in the population. It's represented by the standard deviation or the sigma p plane, all right? The square root of the sigma square. It is represented as a factor influencing plant breeding, the probability that a trait phenotype will be transmitted from parent to offspring. That probability is the heritability. The third core factor is that the proportion of the population selected as parents for the next generation, that is to say, the selection intensity. That's an important factor in influencing the breeding progress, the proportion of the population selected as parents for the next generation. Then finally, I, the expression in units of the standard deviation from the mean and the length of time necessary to complete the cycle of selection. Remember, that I is the same as the K we saw. And the length of time necessary to complete a cycle of selection is the L. And remember, in what we are looking at was over a 13-day period to complete the selection cycle. So here, the breeder's equation traditionally has been part of the toolkit of the applied geneticist for whom results matter and the underlying biological principles are simply secondary. The applied geneticist in this case is the plant breeder. The breeder's equation comes out of applied quantitative genetics, as you can see. That's where the equation comes out of. So in a sense, it is gene blind. It simply describes and projects evolutionary processes or the response selection without any exploration of a deeper framework. But we can obtain the breeder's equation, as you can see. And because of that, it leads to deducting quantitative genetical processes from population genetic theory. And it becomes complex. And at this level of the module, we do not want to explore the complexity. But let us just look at some simplistic aspect of what we are actually saying here. Let's look at the locus and the traits, the genes, the alleles. Let's use a simple counting example. Imagine we have two loci. This could be height, for example, and the compactness of a head of a semi-dwarf variety. Let's say those two loci are locus 1 and locus 2. And so we have that associated with the alleles that they favor A and the big A, and they favor the small a, and they favor the big B, and favor the small b, respectively. So let's assume that A and B contribute 1 unit of a trait. Let's just for that purpose assume so. Then we have the A and B contributing 0 units. Why do we assume so? It's because here the recessive alleles would be masked and so would not be contributing any trait. Remember, we said alleles determine traits. They are trait determining the alleles. So if we additionally expected the phenotypic outcomes to be additive and independent across and within loci, then logically, the AABB are 4 units. Trait, 4 units. The small a and the one big B among the small b and small s should be just contributing 1 trait unit. And then, of course, if we have the AA and the BB, should be contributing the 0 trait units. They're not there. I hope you understand. So let's further assume that the frequency of the two alleles are the same. And we get a little bit into the quantitative genetics here, and where we can assume that P stands for 0.5. If we are into Hardy-Weinberger's equation, we'd understand why the P is 0.5. But for now, let's just accept that as a fact. So within the population, therefore, 50% of the alleles are A and B. And another 50% are A and B at each locus, locus 1 and locus 2. We can therefore construct the following table of genotypic frequencies that segregate within the population, assuming P is equal to 0.05 for A and small a, and for B and small, big B and small b. So we'd get this sort of situation, which if we are looking at the genotypes, we're looking at the frequency, we'd get this. Where are we getting the 16 from? If you had to look at the gametic combination from a Punnett square, if you can remember the Mendelian genetics, then you can understand those proportions that are expressed in terms of the 16. So here, the phenotype additive are those values that we can see 4, 3, 2, 3, 2, 1, 2, 1, 0. And of course, we have the phenotype, Dutch dominance, and we will not want to go into that too much, but just an idea of how we begin to look at the phenotype additive aspect in terms of the genotype and the frequency associated with that. Okay, let's just leave it at that point. What we want to come and do here, please recall, again, I repeat, that additive genetic effects are also referred to as the breeding value. The additive genetic effects, they are also referred to as the breeding value. And so here we are seeing that they are a breeding value, or the additive genetic effects are what they are because they predictably are transmitted to the progeny. It's a predictive aspect. So the breeding value is on a single locus. It represents a single locus example, which is the sum of the average effect of alleles. So if A is equal to 10, and A sub 2 is equal to minus 10, then the breeding value of A1 is equal to 20. You can see you can simply add 10 and 10. Now, if the breeding value of A1 and A2 is equal to 0, then the breeding value of A2 and A2 is equal to minus 20. You get the point? So here, the estimated breeding value is simply the heritability times P, phenotype. So you work yourself into the EBV, which is a function of the narrow sense heritability. That means it includes all additive genetic variants. Then the phenotype P is expressed as a deviation from the population mean. So if we have P is equal to class 3 units, e.g. standard deviations, and the stability is 0.33, then the estimated breeding value is plus 3 times 0.33, which would give us a plus 1 unit. In summary, in case of plant breeding, an increased change in genetic variation can be maximized by a more favorable environmental variability for selective breeding of more responsive lines to high agronomic inputs such as water, irrigation, for example. I repeat that. In case of plant breeding, if we had to exercise selective breeding under high agronomic inputs such as water, then we can increase the change in genetic variation. We can increase the change in genetic variation. And that can be maximized by, therefore, a more favorable environmental variability. You get it? Indeed, breeding for rice and wheat in the Green Revolution was made successful by maximizing more favorable environmental variability. For example, high water input irrigation, that is high fertilizer input. Alternatively, a breeder can increase change in genetic variation. Change in genetic variation, again, by also growing the materials and selecting the materials under stress environment, as long as the genetic variation can still be pulled out of the G by E challenge. As long as the genetic variation can be pulled out of the G by E challenge. Thus, the genetic gain equation does provide a framework for comparing the predicted effectiveness of a particular breeding strategy. The genetic gain equation. It provides a framework for comparing the predicted effectiveness of particular breeding strategies, and is often used as a guide to the judicious allocation of resources for achieving breeding objectives. So I'm going to correct what may have seemed to be implied before when I've referred to genetic gain as the profit of. It is not the profit of that ends up in the final variety. It's the predicted profit that is achievable in particular breeding strategies. Because the ultimate target product is where the farmer will evaluate not the genetic gain, not the change in genetic gain. He doesn't need that. He's not interested in that. He's interested in Easter bean pie. The other profit to talk about would be the profit that derives from selling the produce to get the profit margin up and above the input. And we shall look at that somewhere a little ahead beyond here so that we are not mistaking the two phenomena. Now, I would like to indicate to you again, please, it is highly recommended you listen to the video alongside the PDF lecture notes that I am going to send with the lesson 7A and 7B. You must follow the lectures in sequence. Do not jump from video 2 to video 6, for example. I repeat, do not skip the sequence or else you might miss some aspect you need in order to build on to the next lecture. Because the assessments we are going to get, and they'll be quite intense when we have concluded this. You'll not have to have the time to be checking the notes to answer the formative assessment test. That I will not accept, because then it means you'll now be using the notes to study to answer the formative assessment. It will not be allowed. That's why I'm saying that it will no longer be a situation of getting the tests ready, late at different times. That's when I'm going to announce a particular period of time, date, when we have a particular test and the answers must be in. It will not be like what I did and some people are answering into the next day and the next day because they can now study the notes to answer. You should be doing adequate preparation for the time being. This will conclude this part here so that we will now move significantly into part D. And part D is the last part of the module. It's going to be lesson 8 and so on and so forth. So take note, if we are going to go to part D, the last leg of this module, if you are behind, I urge you to take time between now and next week, because I'm sending this by Friday, tomorrow, the 1st of May. And then you have the Saturday, the Sunday, the Monday, and then I will, after 3 days, go into part D. You don't want to remain behind. And so I would like that we stop at that point, and I will send these notes in due course. All right? And have an enjoyable time.